Will Tipton, warning for you. Hello and good day, everybody. We are continuing with CO62, and we are looking at the variables when adding and subtracting roots. And the good news is, I mean, it's really the same process. You simplify, you look for like roots, just like with fractions, you can only add or subtract when you have common denominators. You can only add and subtract when you have common roots. So the challenge, though, is that you've got to remember how to simplify variables. So if you need a refresher, you can go back to this chart that we had back in CO61 part 2. We know that any variable to an even power is a perfect square. We know that any variable to an odd power will have that extra root x or root y or root n or whatever the variable happens to be. So when we get down here and we're looking at root of x cubed plus 7x root x, what does the root of x cubed simplify to be? Ellen? X root x. Okay? And the reason for that is because we can take out that perfect square factor, that x squared, right? Which becomes an x, and then we have the root x that tags along. And we're adding to that 7x root x, which we can't simplify. We can't do anything with. But can we combine those terms? Yes, we can. Because they both have a root x. Okay? And furthermore, you actually answered both of them. In this case, because we're dealing with variables, our coefficients have to have that like term also. So they both have an x in the coefficients. They both have a root x as the root. Therefore, we can combine them. We have one root x, or one x root x. We add 7x root x's. How many root x's do we have in all? 8x root x. Yes. See? Isn't this fun? No. Well, give it a chance. We just started. We just started. 9 root 12x cubed minus 3 root 27x cubed. Go ahead and simplify each of those. How? Well, it's a good thing we have PO61, where we remember that we can break apart that root 12x cubed into 9 times root 12 times root of x cubed, right? And we can break apart that 3 root 27 x cubed into 3 times root 27 times the root of x cubed. Wait.
How do you do that?
How do I do that? You just math. Split them apart. You just
math.
It's math.
Simplify root 12.
Oh, okay.
Simplify root of x cubed. And again, this goes back to, PO61. Like I said, if we're stuck on PO61, the rest of this unit is going to be near impossible, which is why if you have questions on it, please do ask, right? But we're looking for that perfect square factor for the 12. We have the chart for the root of x cubed, the perfect square factor for the 27, the x cubed again. Yes, Alex?
Okay, so you get an x at the very end.
You do, because of that odd power.
Yes.
Yeah.
So when you add them together, you add an extra 1. So like 9 plus, 18 plus 9, and then you get an extra x.
Let's save that question until we kind of map this out and see if it answers itself.
Oh, okay.
Yeah. Okay. So 9 times root 12 times root x cubed.
I got it.
Very good. We have the root 12, which simplifies to be root 4 and 3 are what we want to use there, that perfect square factor. Okay. Root 4 times root 3, which gives us 9 times 2 times root 3. And we know this x cubed, because we have the chart to help us, is going to simplify to be x root x. Right?
Minus 3.
So there's the breakdown of it. When Alex was explaining his question, he mentioned 18. That 18 comes from 9 times 2. And then because we have an x that's outside of the roots, that x now joins our 18 as part of the coefficient. Because we're multiplying this all the way across, you can multiply things in any order. So we're going to group together what's outside the root, and then group together what's inside the root. You're right. Good. 18x root 3x. For the other one, minus 3 times root 27. The root 27 we're going to break up into root 9 and root 3. That's our perfect square factor. That gives us 3 times 3 times root 3. And again, this root x cubed we know is going to simplify to be x root x. Like I said, the variables are almost easier because it's the same thing every single time. The numbers change, obviously, based on what you have. But 3 times 3 gives us 9. We do have an x to join that coefficient. And then we have a root 3x under the root symbol. Okay? Not too bad. Not too bad. Can we add these? No. I mean, addition. Can we subtract these?
Yes.
Why can we subtract them? They have like terms, right? The coefficients are like terms, 18x and negative 9x. That's in our favor. And they have like roots. Okay? The root 3x and the root 3x. So this is going to equal 9x root 3x. 18x's minus 9x's is 9x's. And then root 3x.
We can't add this. Oh, never mind.
Okay? Ask your questions, please, especially if your questions are up in the simplifying stage, because this is, down on how to do that. But ask your questions here. If you have them. We're actually going to skip down to the fraction.
Let's go.
Okay?
Are we gonna have to do the last one?
We'll see where the day takes us.
Oh.
You think I planned this ahead of time?
Yes.
Okay.
That's not a teacher does.
Can we? That's good. Can we add these fractions the way they are written here?
Yes.
So you have to move the x squared up to the.
So we'll worry about the rationalizing piece when we're all done. If we rationalize in this step, we'll have to do it twice, versus just once when we're all finished. But we will have to rationalize. Elliot's recognizing that this root in the denominator. He remembers you can't have a root in the denominator for a final answer, so we will have to rationalize it at some point, but we're not going to do it quite yet. You do, but if you do it now, you have to rationalize both of them versus just rationalizing one fraction when you combine them. So it's a bit more efficient not to do it yet. Okay? Because we can add these fractions the way that they're written, because like fractions, right? We have those common denominators, okay? And they're common roots. So what is 9 over root x plus 12 over root x? 21 over root x, right? Just like any other fraction, those numerators get added. The denominator stays the same. And as Elliot mentioned earlier, now we need to rationalize. We do that by multiplying by the root in the denominator over itself, which is really just a fancy value for 1. So it's not changing the value of the fraction. But what we're doing is we're removing the root from the denominator. So this ends up being 21 root x in our numerator. Root x times root x is root x squared. The root and the power cancel out. Or kind of the shortcut is just the roots go away. And we have 21 root x over x.
Why would it be root x?
So root x times root x, when we multiply here in our denominator, it gives us the root of x squared. Which, because we're PERMDAS people, we understand that the root and the power cancel out, leaving you with just x. Or you remember that the root of any variable squared is a perfect square,
Yes.
and it simplifies to just be x.
Thank you.
You're welcome. Okay? Let's look at the next one. Can we add these fractions the way they are written?
No.
We cannot. So we go back to our knowledge of fractions, what they are, what they do, how they work. What do we have to do here? Not rationalize yet. Again, that would cause us to do. I mean, could you do it? Yes, but it's still not going to give us fractions that we can add because the denominator still won't be the same. How are we going to get like denominators here, Claire?
I have a question.
Yeah.
Why can't you add them if they're both root x?
Because with fractions, the denominators have to be the same, right? They're not the same. One's a root x, one's a 2 root x, right? Back to fractions, when you first learn fractions, right? 5, 6 plus 1, 6. You can add those because they're the same. Here they both have a root x, which is good, but they're not the same denominator. So how can we make it have the same denominator? Which is going to be what? Multiply the first fraction by 2, right? If we want this to be a 2 root x, how do we do it? We multiply both the 7 and the root x by 2, and that's going to give us 14 over 2 root x plus 3 over 2 root x. Right? I mean, the fraction 14 over 2 root x simplifies to be 7 over 1 root x. You know? So we can do it. We're just multiplying that fraction by 1. We don't have to multiply the other fraction by anything because it's a different fraction. We're just multiplying by 1 here. And it gives us a 2 root x. So now we can add them. Yes? Yes. What is 14 over 2 root x plus 3 over 2 root x? How would you say that? 17 2 root x?
To the square root over third.
I don't even know how that would. 17 2 root x. Something. I don't know.
How do we get
17
the 2
divided by 2 root x.
How do we get the 2 root x on there again?
We got the 2 root x by multiplying our first fraction by 2
Oh yeah.
to get that common denominator.
Yeah.
Okay? Arlene mentioned earlier the whole rationalization piece, and now we do need to rationalize because we have that root down in the denominator, so we're going to multiply. Remember, you only have to multiply by the root you want to remove. We don't have to multiply by 2. Okay? So multiply by root x over root x, and that gives us 17 root x in our numerator. And what is our denominator going to be? Kylie? 2x. How is it 2x, you ask? Well, we have a 2 times 1, so these coefficients doesn't change. It's still a 2. And then root x times root x, just like in this last example here, right? The act of multiplying a root times itself essentially causes the root to go away, right? The root of x times root of x is root of x squared, which simplifies to be just an x.
Yes.
I hear the squeaky chair has found its way back into circulation. Oh, hold on. Hold your question, Lisa. It is school up. Yellow.
Wyatt, give it to me.
Yes. I will for another 3 minutes.
Lucky man.
I will have a class for another 3 minutes at 9:15. Correct. Yep. 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 Sure. Okay, bye. All right. So, Lisa.
What did you add
Damien.
together?
Well, think about fractions, right? You've been dealing with fractions for like 4th and 5th grade. Those denominators stay the same. Okay? There's multiple math rules kind of colliding here, right? We have the rules for roots and the rules for fractions. In some ways, in most ways actually, they're very similar, right? But you got to think about both of them. Okay? We are almost out of time, and so I would like you to attempt the remaining 3
It's hard.
We
We
go over the next one.
for tomorrow.
How do you
We're
get
out of
the
time.
X on top?
on it.
What do you do?
Out of time.
Wait, do you
Okay.
know how to do the rest?
What's that?
What do you do?
That's okay. If you do it wrong, all you gotta do is
Whoopsie.
whoopsie doo